So good evening, students. Welcome to this fourth lecture on communication. And today's topic, as you can see, that it is amplitude modulators, AM modulators. Modulators means the circuits which are responsible to generate the amplitude modulated wave or the amplitude modulated signals. Okay, so there are many types of AM modulator circuits, but we will discuss few of them. And the first circuit is the square law modulation. So in a square law modulation or in a square law modulator, a nonlinear device, you can call it as a PN junction diode. So we have to take one nonlinear device. It may be a transistor, it may be a field effect transistor. Any nonlinear device can be used here, but we are confining ourselves in this discussion with a nonlinear device like a simple PN junction diode. You know that it is a nonlinear device as because the voltage and the current characteristics looks like this. So this is a nonlinear device, and this is specifically a PN junction diode. So in this type of modulator, what we need one nonlinear device, and to the input of the nonlinear device, we are going to add these two signals. These two signals means the information signal, that is MT, and the other one is our carrier signal. And here we have taken the carrier signal form as EC sine 2 pi FCT or EC sine omega CT. Now these two signals are fed to a summation circuit or a summer or an adder circuit, and then the output of this adder will be fed to the nonlinear device. Now after generating or from the output of the nonlinear device, a band pass filter is used. A band pass filter, what is a band pass filter? A band pass filter is specifically a filter which actually gives at its output the specific band which I require. So this will be a band pass filter. So the output of the nonlinear device is fed to the band pass filter, and which is tuned to the frequency of the carrier. Actually it will be twice of the carrier frequency, and then after that we will get the amplitude modulated wave. So it is basically a simpler circuit, a most simple circuit to be used as an AM modulator. So for an AM modulator circuit, basically for the square law modulation, or it is known as the powered law modulation, in this type of circuit we only require a summing circuit, a summer, that is an adder, not an adder amplifier but an adder, and then after that the nonlinear device which I am going to use here, that is basically a PN junction diode, and after that the output of the nonlinear device is fed back to the band pass filter, which is centered around the carrier frequency, and then thereafter we will get the amplitude modulated wave or the AM wave. So now let's move on to derive how this works, and we should explain it by mathematical calculations. So first of all, let's take one information signal as MT, and the carrier wave, as I have shown here, it is EC sine 2 pi FCT. So these are the two signals. That is, number one, the input signal, that is VIT. So if the two signals are MT, that is the information signal, and the other one is EC sine 2 pi FCT. Then after the summing circuit, the voltage form, let it be represented as VI. So that is the input voltage to the nonlinear device, and this will be nothing but the addition of these two voltage waveforms, or MT plus EC sine 2 pi FCT. So this will be the input voltage to the nonlinear device. Now, as it is a nonlinear device, what will be the output of a nonlinear device? The output of, yes, Arindam, why is it called square law modulator or square law modulation? I will be explained after this mathematical deduction is over. So, after the nonlinear device, or the output of the nonlinear device will be V0t. If the output voltage of the nonlinear device is V0t, then it will be given as some constant A1 into VIT plus another constant A2 into VIT, and this is VI square T. So this is the reason what Arindam has asked, that why this type of circuit is known as a square law modulation circuit, and this second order term, that is this square term, actually is responsible for the circuit to be known as a square law modulator. So whenever a nonlinear device is used, as it is basically the simplest form of amplitude modulated circuit, as because only a PN junction diode is used, so this circuit is known as the square law modulated circuit, as because the output voltage of any nonlinear device or of a simpler PN junction diode can be written as in terms of this, that is a constant into the input voltage plus another constant into the square of the input voltage. So now let's put the values, or let's substitute the input voltages here. So it will be A1 into VIT, that is MT plus EC sine 2 pi FCT, and then again A2, and thereafter MT plus EC sine 2 pi FCT whole square. Now expanding this, we will get A1 into MT plus A1 EC sine 2 pi, just the mathematical simplifications, then A2 M square T plus A2 EC square sine square 2 pi FCT, and then the last term, that is twice of A2 MT EC sine 2 pi FCT. So this is only the simplification of the equation written above. Now let's move on to take some. So now the first term I have written is A1 MT. Then take this term, that is A2 M square T. Then A2 EC square sine square, that is A2 EC square sine square twice pi FCT. So we are left with these two terms. So I am taking EC, A1 EC constant, A1 EC as a common term, and then what we have 1 plus, so this will be twice A2 by A1, this will be twice A2 by A1, into MT twice A2 by A1 into MT, and after this will be sine 2 pi FCT, as because sine 2 pi FCT is here for both the terms. So we have A1 MT plus A2 M squared T, then A2 EC square sine square twice pi FCT, and then the last term is A1 EC in bracket 1 plus twice A2 by A1 into MT into sine omega CT. So this is the output voltage of the nonlinear device, or the output voltage from the PN junction diode. Now this expression or this mathematical form or this voltage waveform will be fed to the band pass filter, and which is actually centered around omega c, or you can say 2 pi fc. So it is tuned around omega c, and then what we will find that as this output of the nonlinear device is passed through a band pass filter with a bandwidth at centered at omega equals to omega c to generate the conventional AM output. So the output voltage waveform will just comprises these terms. So the output of the band pass filter will only allow this, that is A1 EC into 1 plus twice A2 by A1 into MT whole sine omega CT. Okay, so this is the amplitude modulated wave which we can form by the amplitude modulator circuit, and this circuit is known as the square law modulator, or this is known as the power law modulation. So Arindam, I think you get your answer. That is, your question was why this circuit is called square law modulation, as because here I have used a non-linear device as a PN junction diode, or I have used a PN junction diode as a non-linear device, and you can see that the relation between the input and output, that is the relation between the input and the output, follows the square law. It follows the square law. So this type of circuit is known as the square law modulator circuit. Okay. Yes, Farhat, good evening. Today you are late, I think. So this is our first modulated circuit, that is the square law modulator or the power law modulation circuit. Okay, is it clear? Do you have any doubts? Okay, fine. Clear, sir. Fine. Thank you. So let's move on to the next circuit. Let's move on to the next circuit. And this circuit is a more complex one, as because we have already discussed the most simplest modulated circuit. Now let's move on to a complex circuit, and that is known as a balanced modulator circuit. Okay, so let's move on to discuss a balanced modulator circuit. Now so this circuit is known as the balanced modulator. balanced modulator. So this is basically an important modulated circuit for the amplitude modulated modulation scheme. Now, as we know that in most of the single sideband systems, we have already learned the single sideband system. We have learned the SSB full carrier, SSB suppressed carrier, SSB reduced carrier. So in most of the SSB schemes, the carrier is totally suppressed or reduced to only a fraction of its original value. Okay. So then by using a filter, one of the sidebands is removed. Hence, as a first step in SSB generation, one has to or we have to remove the carrier. Now using a notch filter, what is a notch filter? Notch filter is an why power law. No, power law, power law means Amor. Here power law means the square. The name is the square law modulation, or it can be referred as the power law modulation. That power is not related to the voltage into current or V square, I square, R. That is not the power here, power consumption here. This is actually as because the circuit is because in the modulator circuit the only device, electronic device, or the basic device is used is a nonlinear device. So, and any nonlinear device, the output and input waveforms or the output and input relations are actually square driven. So that is the square. So the term square law modulator, and as because it is a square circuit, that means it is also referred to as the power law modulated circuit. So this power is doesn't relate to the power consumption or the power consumed by the circuit. Okay. So let's move on to this balanced modulator. As I am talking that in most of the single sideband generation scheme, we have already learned that there are three types of SSB generation. Number one, the single sideband full carrier. Number two, the single sideband suppressed carrier, and number three, the single sideband reduced carrier. So most of the cases or most of the SSB generation, we actually suppress or reduce the carrier. As a whole, we also remove one of the sidebands. So for an SSB generation, so this type of circuit, that is the balanced modulator circuit, is usually used, or it's basically used to generate SSB amplitude modulated wave. Okay. Now here we have to use a notch filter. Now in our previous modulator circuit, that is in our square law modulator circuit, we have used a band pass filter. Now notch filter is actually just opposite to the band pass filter. In a band pass filter, the output is actually selects the band of the input. Certain band of the input is selected at the output. So that's why the filter is known as a band pass filter. And notch filter is generally expressed as a band reject filter. So as you can learn from this particular term, if I use this term as band reject filter, so this is basically in contrary to the band pass filter, it will act in the opposite direction. So for a band reject filter or for a notch filter, the output voltage rejects. The output voltage rejects, or the output rejects a particular band of the input voltage waveform. So that is the band reject or a notch filter. Okay. Now, so using a notch filter to remove the carrier does not work out. Why it does not work out? Because since the notch filter characteristic is such that it also removes some portion of the sidebands along with the carrier. This is due to difficulty in obtaining a very high Q for the filter. Hence, alternating circuits or alternate circuits are developed to suppress the carrier. Now here lies a basic problem. Here lies a basic problem, and this problem is actually related to the filter circuit. As because you have also in your syllabus complete study of filter circuits, but now as you are not acquainted with the filter circuit, so the basic problem for any filter circuit is in ideal case when we are talking about that is a band pass filter or a band reject filter. What does it mean? It means that this is the frequency spectrum of a band reject filter. Now this is the frequency spectrum of a band reject filter. You can think it as this one, and there are two filters in tandem in series. The first filter is the high pass filter. That is rather it is now this is the frequency spectrum. This is the frequency spectrum for a high pass filter, and this one is the frequency spectrum for a low pass filter. I think you got it. So this one, if you can, this one is the frequency spectrum for a band reject or a notch filter. So this one is the high pass filter frequency spectrum. This one is the low pass filter, and this is actually a notch filter or a band reject filter. Now, with reference to these two filters, as these two filters are the basic filter circuits, that is, one is the low pass and the other one is the high pass filter. So you can imagine this this notch filter as it is a low pass filter, and this one is a high pass filter. So if a low pass filter or a high pass filter is connected with the input or with the output of a low pass filter, a high pass filter, so if I connect a low pass filter, and then at the output of the low pass filter I connect a high pass filter, then you can think that this one or this can act as a notch filter. Is it not? Is it okay? So a notch filter can be explained as a low pass filter followed by a high pass filter, as because this one is the frequency spectrum of the low pass filter. This one is the frequency spectrum of the low pass filter. Just consider this part. So this one is the low pass. This one derived from the frequency spectrum of the low pass filter, and this one actually derives from this part of the high pass filter. So if I connect one low pass filter in series with a high pass filter, then it can work as a notch or a band reject filter. So this filter actually rejects this part of the frequency or this part of the bandwidth. Is it okay? Have you understood how I draw a notch filter, or how I can explain a band reject filter in terms of a low pass filter and a high pass filter? Is it okay? Is it okay? Do you understand the operation of a notch filter in terms of a low pass filter and a high pass filter? Okay, so now let's move to this topic, that what you can see here. Now from this part, just remember, just carefully notice this part of the spectrum. Here you find that if you want to, what is your target here, or what is our target here? We want to eliminate one of the sidebands of the double sideband system. So we have to eliminate one of the sidebands, as well as we have to eliminate the carrier itself. Now if this is the frequency spectrum, this is the frequency spectrum of the notch filter. So let's take an example. So in our system, let's think about it, that we have a double sideband suppressed carrier waveform, and the frequency spectrum is, let it be about 2 kilohertz. So from 1K to 3 kilohertz, one of the sidebands is there, 1K to 3K. So that means the bandwidth is twice kilohertz. So we have to remove this part of the frequency spectrum, that is from 1 kilohertz to 3 kilohertz. Let it be look like this. So this one is our carrier, this one is the upper sideband, and here this one is the lower sideband. This one is the lower sideband, this is the carrier, and this one is the upper sideband. Now if we want to generate a single sideband, just think about a single sideband generation. So you have to select either of these two sidebands, whether it is the upper sideband or it may be the lower sideband. So you have to select one of these sidebands. Now say this one is 0, this one is 1K, this one is 3K. So the bandwidth of the upper sideband is around twice kilohertz. So you design a notch filter. Of frequency 1K to 3 kilohertz. So you have designed a notch filter. So from this notch filter, you actually want to reject this part of the total frequency, total band, or total signal. So when you pass this particular waveform within this filter circuit, what you will find that this particular filter, or the frequency spectrum, actually rejects 1 kilohertz up to 3 kilohertz. Okay, that is fine, but this is not the ideal case. It can't reject this way. This is the ideal response. You actually want this type of response. So that means this part and this beyond 3 kilohertz, other signals would be attenuated, or other signals would be removed. But you have find that here some of the signals from beyond 3 kilohertz and below 1 kilohertz, you actually receive those part of the spectrum, of the frequency spectrum. So what does it mean? It means that while removing one of the sidebands, you have actually removed some part of the carrier frequency as well. So while using a band reject filter, or if we use a notch filter to generate this single sideband wave, single sideband generator, that means that actually while removing the single sideband from the entire spectrum, we actually remove some part of the carrier as well. So that is the reason we can't use this band reject filter or the notch filter to produce a single sideband generation wave. Okay, and that is the reason we have to use an alternative method, an alternative circuit, and that is the balanced modulator circuit. Is it okay? Is it okay? Okay, fine. So let's discuss this balanced modulated circuit. So the target of designing this balanced modulated circuit is to remove the carrier wave. Is to, first of all, we have to remove the carrier wave while not disturbing the sideband, because after removing the carrier wave from this double sideband amplitude modulated scheme, after removing the carrier wave, we have two sidebands quietly separated with each other, right? So once, if you consider one sideband, either of the sidebands, that is, if you consider the upper sideband and the carrier, they are separated, or they are quite close to each other, as well as the lower sideband and the carrier, they are also close to each other. So if you at first remove the carrier from the double sideband frequency, then you will find that you have only left with two sidebands while they are largely separated from each other. So after that, by using a filter circuit, you can remove one of the sidebands at ease. So that is the motto, that is the principle of operation here. Now, in a balanced modulator circuit, first of all, I draw the block diagram of a balanced modulator, and after that, I will discuss mathematically how it works. So, this is the information signal. It is fed to one amplitude modulator. It may be the modulator what we have learned just now, that is, it may be a square law modulator. Let's consider it as a square law modulator circuit. Okay, now again you have to consider another AM modulator, and this one is also a square law modulator circuit, but here you have to feed minus of MT, that is the inverted form, with respect to the polarity is concerned. This is the inverted form of the information signal. Okay, so these two amplitude modulator circuit is fed by the carrier wave. Let it be AC cos 2 pi FC t. So this one is the carrier signal, and it is fed to either of the two amplitude modulator circuits. So this what will be the output waveforms? This will be AC cos 2 pi FCT plus MT. So this is MT, and as just now we have already discussed about the square law modulator output, you can readily tell me that it will be this value, that is AC 1 plus MT into cos 2 pi FCT. So this will be the output of the first square law modulator circuit, and here from this second amplitude modulator circuit or the square law modulator circuit, as because here the information signal is in minus MT form, so the output will be AC into 1 minus MT into cos 2 pi FCT. Right? Now just add this, to, and you will be say the output V0, it will be AC cos 2 pi FCT plus AC cos 2 pi FCT. So, and AC MT cos 2 pi FCT minus AC MT cos 2 pi FCT, and it will be twice AC So the output of the balanced modulator contains the two sidebands and other unwanted frequency components. Now these unwanted components are tuned out by the output transformer. So that is the output form, and this will give us twice AC MT cos 2 pi FCT. This will give us twice AC MT cos 2 pi FCT. Now how it works, I will discuss it now. I will discuss how this circuit works. So here the concept is to suppress the carrier component. So let's discuss how mathematically the carrier gets suppressed. Okay. So let's consider the information signal. So this is actually the block diagram, and now we proceed to discuss how the circuit works with the help of mathematical equations, and you will find it more easier then. So let's consider the information signal and the carrier signal. Only these two signals are we need. So if the input voltage to the first modulator, that is the square law modulator, as I am told you. So if the input voltage, that is the information, is Em sine omega mt, and the carrier wave is Ec, sine omega ct. If these are the information and the carrier waves, so the first modulator circuit will have this value as its input, this value as its input, and again the input voltage to the second modulator, that is the modulator which is at the bottom of the circuit, the second modulator. And remember, in this modulator circuit, the information signal or the modulating signal is fed after 180-degree phase shift. So that means the input to the second modulated circuit will be EC sine omega CT, that is the carrier, EC sine omega CT minus EM sine omega MT. I think it is okay to you all. So the first one is the first modulator input. So this is the first modulator input, and this is the input of the second modulator circuit. This one is the input of the second modulator circuit, right? So here EC sine omega CT is the carrier signal, and is EM sine omega MT is the modulating signal. Now, what will be the output of the two balanced modulators? Let the two output or the output voltages of the two balanced modulators, or let the output waveforms or output voltages of the two AM modulators, let it be V1. V1 is the output of the first modulator. Let it be the output of the first modulator circuit, and it will be A1 into the input voltage, that is VIT. So it will be EM sine omega MT plus EC. A1 EM sine omega MT plus CT plus A2 EM sine omega MT plus EC sine omega CT whole square. So this will be the output voltage. This will be the output voltage of the first AM modulated circuit. That is A1 into input voltage plus then A2 into the input voltage square. Okay, now let us write the output voltage for the next or the second AM modulator, and it will be A1 again. So it will be EC sine omega CT minus EM sine omega MT. So it is A1 into the input voltage, then the constant A2 into the input voltage square. So EC sine omega CT minus EM sine omega MT whole square. So these are the two output voltages. These are the two output voltages for the two AM modulator circuits. Is it okay? Let these equations, let's write these equations as equation 1, equation 2. This one is our equation 3, and this one is equation 4. So equations 1 and 2 are the input voltages, of the AM modulators. Equation 1 is the input voltage for the first AM modulator, and equation 2 is the input voltage for the second AM modulator. Later on, equation 3 is the output voltage of the first AM modulator, and equation 4 is the output voltage of the second AM modulator circuit. Is it okay up to this? Any doubts? Okay, fine. So, so now let's move on to that. Let these equations be reduced as let us put em sine omega mt. Just for simplicity, let us take em sine omega mt equals to m, and ec sine omega ct can be written as, say, c. So let these equations reduced somewhat, otherwise it will take a lot of amount of time. So now these equations, that is equations 3 and 4, can be written as V1t equals to A1 into C plus M plus A2 into C plus M whole square, and equation 4 can be written as V2t equals to A1 into C minus M plus A2 into C minus M whole square. So just write this and you can see that these equations reduced great. So let's write this equation 3 and equation 4 as equation 3 turns to V1t equals to A1 into C plus M plus A2 into C plus M whole square. Let it be equation 5, and equation 4 can be rewritten as V2t equals to A1 into C minus M plus A2 into C minus M whole square, and let it be equation 6. So these are just the simplified forms of equations 3 and 4. Just we simplified these equations. For our simplicity, we have taken this. Okay. Now what will be the output of the final circuit? So what will be the output? Constant A1 and A2 be same in V1, V2. Yes, yes. This will be same. This will be the same, Uday, as because the two circuits, that is the two modulated circuits, are used are similar to one another. So these constants are these constants you can regard, you can consider these constants as the same. That is A1 and A2. Okay. So now the output voltage will be the difference of the output voltage V0t will be the difference of this V1 and V2. So we can consider it as V1t minus of V2t. So what happens? Just if you consider 5 minus 6, that means A1C minus A1C. So A1C cancels, A1M plus A1M. So it will be twice of A1M, and then A plus B whole square minus of A minus B whole square. That will give you, that is 4 AB, and if you have 4 A2 into Cm, or 4, you have 4 A2 into Cm or Mc. You can write it as you wish. So this will be the output voltage. Now just put these values of M and C here, and you will find twice A1 into Em sine of omega mt plus 4 times A2, and then M into C, that is Em Ec sine omega mt, then sine omega ct. Let it be equation 7. So this is the output voltage form. It is V0t equals to twice A1 Em sine omega mt plus 4 A2 Em Ec sine omega mt into sine omega ct. Is it okay? Okay. Now from this equation 7, what we find? We find this one. This one is the modulating signal. This one is the modulating signal. And the second term, of this equation, we can write it as twice A1 into EM into sine omega mt plus twice A2 EM EC into twice sine A sine B form. We can write it in twice sine A sine B form. Right. Now, what is twice sine A sine B? Twice sine A sine B means that is cos of A minus B minus cos A plus B. So you will find this equals to twice A1 EM sine omega mt plus twice A2 EM EC cos A minus B, that is cos of omega C minus omega mt. It will be cos A minus B, that is omega C minus omega mt minus cos A plus B, that is omega C plus omega mt. So you can find this, or you can write this equation 7 as in this form. Now if you take twice A1 equals to capital A. If you write twice A1 equals to capital A and twice A2 EM EC, twice A2 EM EC as capital B, we have, if this one is capital B, so we can write it as A into EM sine omega mt. We can write it as A into EM sine omega mt. So this is the information signal, this is the modulating voltage plus B, and then cos omega C minus omega mt minus of cos omega C plus omega mt. Can you see this last line? I think not. So let's write it again here. So the output voltage will be, looks like A EM sine omega mt plus capital B. That capital B is actually twice A2 EM EC. So it has B cos omega C minus omega mt minus cos omega C plus omega mt. Let it be equation 8. So this is the final output, of a balanced modulated circuit, and you can see that under an ideally symmetrical condition. Why I am talking about the ideally symmetrical condition? Here two terms are used. Number one, the ideally, and the other one is the symmetrical condition. So as I think Orindam has asked initially, that constants Uday has asked that constants A1 and A2 be same in V1 and V2. Actually, then I refuse to answer this, as because that if you consider, you have to make sure that in electronics no device is symmetrical, or no two devices are identical with each other. You can't find two PN junction diodes identical to each other. You can't find two bipolar junction transistor identical to each other. You can't find two op amps identical to each other. So identically or symmetrical devices are just impossible in electronics. Okay, so that's why if I consider the constants A1 and A2 for both the cases V1 and V2, it is actually faulty. But then why I have taken this A1 and A2 in both the cases? To just simplify the mathematical expressions. And again, here I am talking about this part, that this is under identical symmetrical, or rather ideally symmetrical conditions. So if two amplitude modulators, if two square law modulators are identical to each other, that is impossible. In reality, that is impossible. But here in theory, we assume that these two amplitude modulators, modulator 1, modulator 2, are ideally symmetrical to each other. If this is so, if these two modulator circuits can be taken as ideally symmetrical, then you can find that the carrier wave is removed. Then you find that the carrier wave is removed, and here you have not used any filter circuit. You have not used any filter circuit. What we have used two identical modulator circuits. Now you may ask that if these two modulated circuits are ideally, that means in practical, in real life, this will not be available. So then what happens? Then you can't remove the carrier wave entirely. You can't remove the carrier wave entirely as it is done, or as it is shown in equation 8, as because these two modulators are ideally symmetrical, and that is why they cancel the carrier wave each other. Now from this theory, the essence what I am going to convey, that you have to take two ideally, as much ideally symmetrical or as much symmetrical devices you find. You have to take two diodes while constructing two A modulators. You must consider as much possible symmetrical diodes you have to use. So you have to use two similar family diodes. Okay, but that doesn't mean that these two diodes are ideally symmetrical. Okay, so that doesn't mean, but that can reduce the difference between these. That can reduce the difference between these, as because these two members or these two diodes are from the same family. So it can reduce a lot, or it can remove the carrier maximum. But if you want to remove the entire carrier, you can't do it from this circuit right now, as because in practical life, in reality, two electronic devices cannot be symmetrical with each other. But in theory, here we have assumed that this is an ideal case, and we have two symmetrically matched, or we have two ideally matched modulated circuits. And if you have two balanced, or if you have two matched A modulator circuits, you can remove the carrier as a whole. Okay, so from this particular equation, what we find that under an ideally symmetrical condition, the carrier gets cancelled. And what we have in this equation, we have only the side bands. We have only the side bands, that is the lower side band and the upper side band, and the modulating signal intact. The modulating signal, that is a em sine omega mt. Okay, now after this, if we use a tuned circuit, it can remove that modulating signal, it can remove the modulating signal and allows only the two sidebands to appear. Only the two sidebands to appear. So after this, here we have a target. We have initially a target to remove the carrier, as a whole, and from this particular balanced modulator circuit, we can remove the carrier entirely. Okay, but that is due to the ideally symmetrical modulator circuits we have used. But we can remove the carrier as a whole, and entirely the carrier is absent here. You can find it in this equation, and we have only the two sidebands. This one is the lower sideband, this one is the upper sideband, and this one is our information or the modulating signal. So after this expression, if you want to remove this information signal, keep it with yourself, then we have to pass this voltage waveform via or within a tuned circuit. While in the tuned circuit, this particular modulating signal or this particular modulating voltage is removed, and then we only left with the two side bands. So that is the way to create single sideband amplitude modulated waves. And by using this simpler circuit, that is here, as you can see here, only two amplitude modulators, that is, it may be square law modulator circuits, and the square law modulator circuits are the simplest one. So you have to use these two simple square law modulator circuits, and after this you can remove the carrier wave entirely. You can remove the carrier waves, and you have left only with the two side bands as you desire. Okay, so with this I am concluding this topic, that is the amplitude modulators for an amplitude modulation system. Okay, so in our next class we will move towards the amplitude demodulator. So after modulator, that means we have already generated, or we can produce the amplitude modulated wave as we have learned from our theoretical aspects. Now we have applied it into the circuits, into the electronic circuits. So now we have designed, we know how to design the single sideband wave, how to design the double sideband, that is from our initial first circuit, that is the square law modulator circuit. And after this balanced modulator circuit, we actually know how to generate a single sideband amplitude modulated wave. So after this, the next topic will be to demodulate the circuit, to demodulate this amplitude modulated wave. So the demodulator will be inside the receiver. So we have completed the transmitter part, and after this part we have only left with ourselves is the receiver system, in which this wave after transmission, it actually receives by the receiver, and in the receiver part actually a demodulator will be there, which demodulator detects the original voltage, original waveform, that is the information signal, and then the entire communication or the entire amplitude modulation scheme will be completed. So till then, thank you.